This is Team 71's design of Team 70's most beautiful machine, an ankle biter.
For our most beautiful machine, we were tasked with creating an ankle biter. This ankle biter should locate the nearest floor-level object and proceed to run into it without damaging itself. The desired operational range was with the nearest object being between 5 centimeters and 1 meter from the ankle biter. After some time developing our ankle biter machine, we would ask for further clarification on robot speed and size. Our answers were simply to use full motor speed potential and to not make the robot too big. With all of this client information, we would determine our engineering specifications.
Team 70 outlined 5 customer needs. For the first, finds closest object, we established a technical need of correctly finding the closest object. From there, we found the technical requirement and target value of correctly identifying the closest object 50% and 75% of the time, respectively. For the second customer need, collides at speed, we determined that the technical need was to collide with a high motor speed. For this, we found that the technical requirement and target value were the motor speed equaling 100 on impact. For the third customer need, does not take damage, we determined that the technical need is for as few Lego pieces as possible to fall off on impact. We determined that the technical requirement and target value for this technical need are less than 5 pieces coming detached and less than 2 pieces coming detached on average, respectively. The fourth customer need, which is not too massive in size, was determined to have a technical need of having reasonable size within all 3 dimensions. This led to a technical requirement of fitting within a cube with 100 centimeter sides and a target value of fitting within a cube with 50 centimeter sides. The final customer need was given as senses objects up to 1 meter away. This functions as the technical need, technical requirement, and target value, all being senses objects up to 1 meter away.
So for the design process, we decided to split up the 2 main components of the design, the programming and the building, into 2 separate components. And basically we just tested it as it was developed to make sure that they both worked together and performed as expected. So for example here, the initial hardware decision to use the BrickPi ultrasonic sensor was changed due to the software side having better success with the GrovePi ultrasonic. So for the system diagram, it's pretty basic. The power and program was supplied to the Raspberry Pi, which then sends that information to the sensor and the motors, and the sensor takes in the environment, and then basically the motors respond depending on how it senses the environment, and then takes the vehicle to the closest object and bumps it with the according speed.
Analysis of alternatives. The first important feature of our robot was its locomotion, or ability to get to where it was trying to hit. We decided to do this by using independently spinning wheels, each with their own motor. Some alternatives to this would have been using treads or connecting the wheels in some fashion. However, we found that this design gave us the most control over how the robot moved, which was very important. The next important feature of our robot was sensing the closest object. We decided to do this by attaching a GrovePi sensor to the front of the robot and having it spin around. Some alternatives to this was to be using a BrickPi sensor or to spin the sensor around instead of the robot. However, both of these were too unreliable, so we went with this design. Finally, the sturdiness of the robot was very important as it was running into things. To ensure that nothing broke, we placed the sensor behind the front wheels, which allowed it to not have an impact when it ran into whatever obstacle it was running towards. An alternative to this would have been to place a brace in front of the sensor. We determined that this was not necessary as there was no damage being done to the sensor in our tests. Evidence system means specification. For each of the engineering specifications we laid out, we conducted a series of tests to ensure that we met that standard. To ensure that the robot correctly identified the closest object 75% of the time, we simply ran the code 10 times and found that the robot correctly identified the closest object 9 of those 10 times, or 90%. To ensure that the robot moved fast enough, we simply set the motor speed to 100, and this was sufficient for all of our tests. To determine the number of pieces falling off on impact, we used the dataset from our 10 trials that we used to identify the correct object and simply allowed the code to run to completion and found that only 3 pieces fell off throughout the 10 trials. Our final robot design was smaller than the maximum size that we'd laid out, and we were happy with this. Finally, to ensure that the robot worked up to 1 meter away, we completed 3 trials of the robot at 1 meter away from the target, and all 3 of these trials were successful.